Right. Wonderful people, let us look at something that is also very interesting. And this is called rate of change and the derivative at a point. Now, remember the expression f at xo plus h minus f at xo all over h if h is not equals to 0. Now, remember this expression. It is an expression because there's no equal sign here. Remember that this expression is called the difference quotient. The difference quotient, because there's a division line there. This is called the difference quotient of f at xo with increments of h. I've already explained that. If the difference quotient has a limit as h approaches 0, that limit is given a special name and notation. Now, the derivative of a function f at a point xo is denoted by this, f prime of xo. What is this? This is the derivative. Very important. This is called the derivative of a function at a point xo. And the derivative of a function at a point xo is equals to the limit as h tends to 0 f at xo plus h minus f at xo all over h, provided that the limit exists. This is so important, wonderful people. This is so important. Now, the derivative has more than one meaning. This is something very important for you to know. The derivative that you see here has more than one meaning, depending on what problem we are considering, because the meanings can be different. The formula for the derivative is the same as the formula for the slope of the curve y equals f at x at a point. If we interpret the difference quotient as the slope of a secant line, then the derivative gives the slope of the curve y equals f at x at a point P with the coordinates xo and f at xo. If we interpret the difference quotient as an average rate of change, the derivative gives the function's instantaneous rate of change with respect to x at the point x equals xo. I want us to understand this. We are saying the derivative has more than one meaning. Depending on what problem we are considering, the formula for the derivative is the same as the formula for the slope of the curve y is equals to f at x at a point. If we interpret the difference quotient as the slope of a secant line, the first meaning, if we are dealing with the slope of a secant line, then the derivative gives the slope of the curve y equals f at x at the point P, xo and f at xo. This is what we have been dealing with here. Interpreting what now? Interpreting the derivative of a function as a secant line. The first application here. If we are dealing with a secant line, the derivative gives the slope of this curve at the point this. Right. If we interpret, secondly now, if we interpret the difference quotient as an average rate of change, can you listen to this now? If we are dealing with the average rate of change, then the derivative gives the function's instantaneous rate of change with respect to x at a point x equals xo. Right, let us try to study this interpretation. And because we saw the one application of a derivative of a function with respect to a secant line, now we are going to look at the derivative with respect to the instantaneous, instantaneous rate of change. Right. Now, let us look at one example that might give us an idea as to this. Now, suppose the question comes and say, suppose it comes and say, the rock fell based on the equation y is equals to 16t squared. Let's say the rock fell based on the interpretation and the movement of the rock is given by the equation y equals 16t squared feet during the first t seconds, and we used a sequence of average rates over increasingly short intervals to estimate the rock speed at the instant t equals 1. This is something that I dealt with in my tutorials. If you go and look at the average rate of change in a graphical representation where we use a table of values, you might get an idea as to what is happening here. This is the Galilean approach, when Galileo wanted to measure the speed of a falling rock at different time intervals. I interpreted this in my tutorials, and you might want to go to the lectures of Papa Fanzo in differential calculus to check exactly how the table looks like and what sense it made. So I'm not going to deal with that in here. This is just a revision. Right, so we are saying the rock fell based on the mathematical equation that describes the motion of the rock, y equals 16t squared, the Galilean equation, feet during the first t seconds, and we use the sequence of average rates over increasingly short intervals to estimate the rock speed at instant t equals 1. That's exactly what we did in that previous tutorial. Now the question says, what was the rock's exact speed at this time? At which time when t was equals to 1? So we don't know, we don't want to say when it was approaching 1 from the left or from the right. We want to know the speed exactly at 1. Right. Now, what will be the solution for this? Okay, remember we are given y equals 16t squared, so we are going to differentiate our y with respect to t. So I'm going to say f at t is equals to 16t squared. Okay, that is fine. And remember what they said, the average speed of the rock over the time intervals. Now, one most important thing, remember they said what was the rock's exact speed at this time, at exactly t is equals to 1. So I'm going to say the average speed of the rock over the interval between t1 and t1 plus h seconds, where remember this h is just a minimum increment, which remember they are the increments of t. So I'm going to say, okay, I know it is at t equals 1, and I'm also going to say at t equals 1 plus h, where this is the increment from 1 to t on the x-axis. I think we dealt with this in here. So the movement from here to there, I'm not going to say this is remember here this is your xo, this will be your xo plus h. Please try to remember that, because when I say f at xo, I simply mean we're going to substitute this into the equation to get that, and the gap between this and this is x plus h. To get here, you must add h to xo. So hence I'm doing the same. I'm having t1, I want to move to another point, so this would be something like this. This is 1, and the difference here moving there to here will be 1 plus h. right? But h, remember, it's just a tiny difference between this point and that point, because this is heading towards that, or that is heading towards this, such that h is made so small that a has a very minimum influence on that. Please let me not go deeper into this. Please let me just arrive at what I want to say there. Right, so if h is positive, of course we are moving from left to right, and it will be positive because it is bigger than this. We can do the following. Based on the principles of the limits, we can say f at, remember, xo plus h, that will be 1 plus h. If we interpret this as the final value, we can say this is q, we can say this is p, just for you to understand. And then we can minus f at 1. Remember, we are told at t is equals to 1. So this would be your final, which is this, and this would be your initial. Please see it in that way. Don't see it as this being the function y equals negative 16t squared. No. We are dealing with an instantaneous rate of change, not a secant line. Please. So you have this minus this. Remember, this is very important. Divided by h. Right, and then I want you to see something here. I haven't substituted the function, which is what? Which is this. I haven't substituted the function there. So I'm going to proceed and say, where I see f, I'll be writing my 16 now. 16, and I'm having this 1 plus h, that is squared. Please be very careful. This is squared. And then I'm going to minus 16 into, I can substitute my 1. I have my 16. Where I see t, I'm writing 1. That needs to be squared. I couldn't resolve this immediately because this is not 1. This is 1 plus h. Please try and see this. I can divide this by h. And what is it that I will get there? If I try to simplify this, I will have 16, 1 plus h, 1 plus h, minus 16 all over h, and I might get 16 into 1 plus h, that will be 2h plus h squared minus 16 all over h. And let me just come this side so that we see. Now from here, what is it that I can do? I can multiply everything by 16 in here, so that I have 16 plus 32h plus 16h squared minus 16 all over h. So please don't forget that. This times this, this times this, this times that will give you this, and you still have your minus 16. Right, from here, positive, negative goes out. I have a common factor of h. 32 plus 16 h all over h. Let's get rid of those two. 32 plus 16h. We can allow this to now approach 0. And if we do that, we would get a value of 32 feet per second. This is very, very important. Right, having that, what does that really mean? What does that really mean? Right, remember what the question was saying. The question was saying, What was the rock's exact speed at this time? At exactly t is equals to 1. The speed, remember this is 1 sec. Time is measured in seconds here. That would be 32 feet per second. That would be the speed exactly at t is equals to 1. Now, let us try to summarize this so that we may finish up this. Right. We see that we have been discussing slopes of curves. That's exactly what we did. Lines of a tangent to a curve. We spoke about this. The rate of change of a function and the derivative of a function at a point. We dealt with all this. All of these ideas are based on the same limit. Right. I want to draw up your attention to the following. So the interpretations for the limit of a difference quotient is that the limit as h approaches 0, f at xo plus h minus f at xo all over h. Now the first thing to note here, the slope of the curve y equals f at x is equals to xo. This is the first thing. The slope of y equals this at a point x equals xo is given by that. Secondly, slope of a tangent line, the slope of a tangent line to the very same curve y equals f at x equals xo is also given by that. Thirdly, the rate of change of the function f at x with respect to x at x equals xo is also given by that. And lastly, the derivative f prime at xo, f prime xo at x equals x0 or xo is also given by that. So what does this tells us? It tells us that if you want to find the slope of a function at x equals x0, you use this, provided that the limit exists and h is not equals to 0. If you want to find the slope of a tangent line to a curve, this at x equals x0, you are using that. If you want to find the rate of change of a function f at x with respect to x at x equals xo, you use the limit. If you want to find the derivative of x0 at x equals x0, you use the derivative. And that will bring us to the end of our lesson for today.